Hi there everyone, welcome back to the channel. I'm the GCSE science teacher, and in today's video we're going to be learning about waves, which is a topic found in GCSE Physics. If you do enjoy this video, let me know by giving it a thumbs up, share this with someone else, and please do subscribe. Thank you so much, by the way, to everyone who has subscribed. It's amazing. So many of you have joined this community, and we are so close to 1,000 subscribers here. So if you know of anyone that would like more science support, maybe biology, chemistry, or physics, let them know about this channel, share it with them, and hopefully we can continue to grow as a community and share just our passion and excitement for science as we already are starting to do so. So I hope your GCSEs are going well if you're currently studying them and you have exams soon. I know a lot of you are going to be doing your paper 2 sciences very soon, so best of luck for those. I will link some revision for you at the end of this video and in the cards and in the description box if you need any help. Also, feel free, if you have any video suggestions or queries about any of the topics that I've done so far, or you would like certain topics to be covered here on YouTube, let me know and I will definitely get round to those videos for you. Anyway, let's get started. So what are waves? Waves are a oscillation or a vibration at a fixed point, and they essentially transfer energy, which is measured in joules, but they don't transfer matter. Now, we can actually observe this quite nicely if we got a piece of string and we were to move it up and down with our hand. And there's an example here you can see here. You can see that those waves would start to be visible. Now, if we got a tiny bit of sellotape and we stuck the sellotape down onto a piece of that string, indicated here by that little yellow patch you see there, if we were to move the string up and down still, that sellotape won't actually transfer, that matter won't transfer. It's just moving that string, moving that sellotape at a up and down motion, the vibrations at a fixed point. So that's the key definition you should know. Now, there are different types of waves. There's lots of examples of waves. In fact, you've maybe come across waves before in your everyday life. So, for example, sound waves, the reason we can hear things are due to waves. It's how Bluetooth works with wireless devices. We also have it in medical settings. So, ultrasound, when people are looking at soft tissue organs or maybe during pregnancy. We even have it to image certain bone structures as well in the case of x-rays. But yeah, UV light is around us, so is visible light. So waves are essentially everywhere and make up a lot of the world as we know it. So we're going to talk about the different types of waves. And as you can see with the examples I've given, like sound waves, ultrasound, electromagnetic waves, I've put little letters next to them, L or T. And this is talking about the two categories of waves, which we're going to come on to now. So longitudinal for L and transverse for T. So let's talk about it. So like I said, we have two types of waves, two categories called longitudinal and transverse. Now, when we think of a wave, if I asked you to just draw a picture of a wave, most of you will do this up and down motion, if not everybody, okay? And this is because a typical wave is this transverse wave shape, this up and down squiggly motion. And that's what we tend to think of when we think of wave structures. However, we also have longitudinal waves, and they have a slightly different structure, which we're going to talk about. So let's start off with transverse waves, okay? It has a typical wave shape, T for typical, T for transverse. So some of the different labels you can see here, we have a peak or a crest, which is the very top of that wave. We also have a wave length, which is measured in meters. And as the name would suggest, it's essentially the length of that wave, that full wave pattern. So it goes from one part of the wave to the next sequential part that comes after it. So it could be from peak to peak or crest to crest. It could be from trough to trough. It's just showing you that entire wavelength. We also have the trough, as I've mentioned. So if any of you are animal lovers, maybe you like horses or domestic animals, you'll know that a trough is like a bowl that you feed an animal with. Okay, you give them food inside, and a trough has that kind of bowl-like shape. You can see that on the transverse wave. It has that sort of bowl shape, and that's where we find the trough at the bottom of the wave. Now, we also have amplitude, and you may have heard of amplitude in the case of, well, first of all, you may have heard of it in the case of how loud something is, if you amplify something. But in this case, amplitude is just the height of that wave, and you can see that there. Now, the other type of wave we have is the longitudinal wave. So although there are slightly different labels here, you can also see that a longitudinal wave also has that wavelength structure. So from one point of the wave to the next point on the same wave from the same point. So, for example, peak to peak in a transverse wave, or you could go from rarefaction to rarefaction or compression to compression in a longitudinal wave. Now, what do those two words mean? So, compression is when the waves are very, very close together. The frequency is high. You can see they're compressed, they're squashed together. Whereas rarefaction is when you have slightly more spreading out of those vibrations. And that's the key difference there. Now, if they ever ask you a key difference or a key definition for longitudinal and transverse waves, you need to know the following. So, longitudinal waves are vibrations that are parallel to the direction of travel. So, if you look at the example here, we have a slinky and someone is moving it back and forth. So, they're literally pushing it away from them and pulling it towards them. If you do that, you'll see the slinky extending or rarefaction, and you'll see it coming together, all those compressions. And that's because those vibrations that you're forming, they're actually moving away from you and towards you. And that is because of that wave travel. So it's parallel to the vibration. In the case of transverse waves, however, if you were to get that slinky again and you were to move your arm like up and down like this, you'd actually find those waves forming that transverse wave pattern. And as you can see, the waves are moving upwards and downwards, but the wave is moving away from you as well. So therefore, transverse waves have vibrations at right angles to the direction of wave travel. And that is the key difference you need to know. Okay, so wave characteristics, there's two specific keywords that you need to know the definitions of. So the first one is time period, and this essentially is the time taken for a full cycle of that wave. And frequency is the second word, and this just means the number of waves passing a point each second. Now, the way I like to think about this is if you've ever caught a bus before and you're waiting for the bus to arrive, you'll know that your bus will arrive every 10 minutes, or the frequency of that bus is every 10 minutes, whereas the time taken is the 10 minutes. That's the time period. So essentially, frequency and time period, they are very much interlinked. And we're going to talk about some of the maths behind this as well. Now, just to help you out in the exam, they could ask you to draw a wave as a result of different characteristics. So they could say, here's a wave, now draw what it would look like if the frequency increased or the amplitude increased or the wavelength decreased. And you'd have to manipulate the shape of that wave on a graph to show that. So it's really important you understand what those different waves would look like and the characteristics and how they would feature as well. So I've got two waves here, and you can see that the top one has a lower frequency than the bottom one. It also has a longer wavelength. They both actually have the same amplitude. The height of that wave, where the peak is the same. Something else to mention, you can see the one at the bottom has a much higher frequency. So remember, frequency is just the number of waves per second passing a certain point. So here are the calculations that you need to know for your exams. There's two particular equations they like you to use and also manipulate and rearrange if needed. So the first one is looking at how time period and frequency are related. Now, they are inversely related. So if you increase time period, you actually decrease the frequency. And you can see this as time period t is equal to 1 over f, the frequency. Notice time period is also measured in seconds and the frequency is measured in hertz. Just be careful of units when you are writing your answers. The second equation is showing a relationship between wave speed v, which is often a symbol for velocity, so speed and velocity. We also have wavelength and we have frequency. Now notice that wavelength is actually given the symbol lambda, which is a Greek letter. Don't let that throw you off. It's just a simple symbol that just illustrates wavelength, okay? So nothing unusual here, just a symbol for you guys to recognize as wavelength. Now, speaking of wavelength, because it's a length, it's measured in meters. The frequency we know is already measured in hertz, and the wave speed is measured in meters per second, which is often used for speed and velocity. Now, did you know the speed of sound in air is actually 330 meters per second, which is incredibly, incredibly fast. However, the speed of light, visible light, is much, much faster. And if you can tell me what that is, if you know it, let me know in the comment section. I'll also write the answer in the description box as well. So in this particular situation, if you found yourself having to calculate the frequency, the wavelength, the speed, the period of time, these are the equations you can use. Obviously, as well, you could manipulate these equations to combine them. So obviously, if you know what the wave speed is and the wavelength, that could be substituted in for frequency in the time period equation. So you can combine these equations too. And like I said, you could be asked to rearrange them. So definitely worth having a practice of some of these. So here is a practical method that nicely illustrates those calculations we've just talked about in an experimental form. So the key aim for this experiment is to measure and calculate the frequency, the wavelength, and the speed of waves on the surface of water. Now, remember, water waves or ripples on the surface of water, these are examples of transverse waves. So what we expect to see are really clear transverse waves that have that typical wave shape. Now, what you need to do in the first instance is use a ripple tank. And as you can see here, this has essentially a tank that's filled with water. You're going to fill it to around 1 inch or a few centimeters deep of water. And you're going to place a wooden rod on the surface of that water. And this will help create those ripples. Now, you can move the rod back and forth yourself. However, often we will use a motor or a generator to actually help make the waves produced easily and also kind of make them consistent as well. You want to make sure that they're low frequency waves so you can really see the wave pattern clearly. What you're going to do is you're going to turn the light on that's above the ripple tank, and what will be projected are the shadows of those waves. And on the floor or on the surface, you might want to use some white card to make it look really clear and crisp, and you'll be able to see the wave patterns. Now, what you're going to want to do is when you see those wave patterns form, you want to measure the length of the waves and then divide the number of waves to record the wavelength. That's the first thing you want to do. And then you also want to count the number of waves passing a point every 10 seconds and then divide it by 10 to record the frequency. You can also then calculate the speed of waves by doing frequency times the wavelength as well, like we talked about before. Now, the one thing with this practical is if you are doing this and the waves are moving, it's quite difficult to actually see what's going on. So you might want to take a photo of the waves that are formed and then use that photo to calculate the frequency and the wavelength as well. And from there, you can calculate the wave speed. One thing I will say though, just make sure you do lots of repeats, calculate the mean average of those results that you're recording, and therefore you get a more reliable picture of what's actually going on. Remember as well, any calculations you do, always make sure you write the units so you understand the quantities that you're working with, and that will really help strengthen your method when you are sharing your results. And that's it from me today. I've been a GCSE science teacher and you have been curious. If you did enjoy this video, let me know by giving it a big thumbs up. Share it with someone else in case they would like to revise paper 2 content for physics. I know that exam is coming up soon. So if you know of anybody that would like more support with GCSE sciences, definitely let them know about this channel. Share this video with them. I will also link for you guys in the cards or in the description box or at the end of this video the paper 2 topic revision that we did recently here on my channel, all for biology GCSE. So if you would like a short condensed version under 30 minutes of revision for paper 2 biology, that video will be available for you. Chemistry and physics paper 2 videos are also coming out soon, so keep an eye out for those. And if you don't want to miss them, please do subscribe. We are so close to reaching 1,000 subscribers here. So if you'd like to join this community and you know of other people who would, bring them over, join this community, and let's talk about science. Have a fantastic day. Take care, and I will catch you in the next one.